Hey there folks, Mr. D here, and in this video we are going to continue talking about periodic functions, and then that is naturally going to lead us into the unit circle. All right, this will make more sense in the units to follow. We're really just going to be dipping our toes into the unit circle for this unit. Unit circle, that's fun. You're really going to be going much more in depth in pre-calc, but purpose of today is just to kind of like build our familiarity with angles, and then when we see the unit circle, it's not going to be too scary. Before we get into the new stuff though, the previous worksheet, if you guys want or need to see some of these responses, feel free to pause the video here so you can take a look. Just as a quick heads up, your functions for 4, 5, and 6 might have looked different. You just had to sketch some periodic function. You could have gotten as wonky as you wanted with those patterns. It doesn't have to be a zigzag or a perfect curve. It can be any repeating pattern. All right, here's the backside. Here's a perfect example of one of those little wonky patterns I was talking about. I don't think I'd want to try to replicate that. All right, let's get into our warm-up. So, let me zoom into the actual question here. We have Mary rides her bicycle along a flat road at night. Ian can clearly see a reflector, so here's the reflector. You can clearly see a reflector on the spoke of her wheel rotating. Now, it's important to note, this reflector is kind of inside the wheel. It's not on the very edge. All right, so that little reflector is not on the very edge of the wheel. Ian notices, as one typically does, that the reflector is closest to the ground when time is 0. Can we just take a moment to notice kind of how strange this problem is? We have some dude, Ian, is just watching Mary ride a bicycle at night. And, I mean, that's not setting out funny red flags? Come on, math textbook writers. What's going on here? All right, he measures the height of the reflector above the ground at different times. Again, as one typically does when they watch people ride bikes at night. All right, so they kind of give us an image, but what I'm going to do is I'm going to sketch that. Let me find some blank space down here. Hey, blank space, Taylor Swift, gotta love it. And then we're going to fill it in based on the information given. So I've got my overall tire, but then within there I've got the reflector. So we're going to have that goes around. And what I like to do here is I'm going to figure out how long does it take to go around. And then as soon as I know that time value, I can figure out kind of halfway. So let's say this was 10 seconds, this would have to be 5 seconds. Or if this was 100, this would be 50. And then I can figure out kind of the quarter seconds. This will help me kind of establish the midline. All right, so let's take a look. We've got height 6, 12, 18, 24, 18, 12, 6, 12, 18. I'm assuming it would go 24, 18, 12, 6. So it looks like it repeats at 0.6. So it takes 0.6 seconds to get back from where it started. All right, so this would be 0.6 seconds, which means this up here would be 0.3 seconds. And I don't know if I'm going to need it, but I'll put it in here anyways. This would be 1.5 seconds, and then this would be 4.5 seconds. All right, cool. Now what we need is the heights. So we want the low height and the top height of this reflector. Okay, so the lower height and then the top height, so the min and the max essentially. And then that's also going to help us figure out the middle. So let's take a look. The lowest height I'm seeing would be 6. The biggest is 24. So 6 and then 24. Now, if I know the minimum and the maximum, I can figure out the middle. So I can figure out what number is smack dab in between 6 and 24. Essentially, I'm just going to take the average of those two numbers. So add them together, chop it in half. I would get 15. So the axle of this wheel is 15, what are we in, inches? Yeah, 15 inches off the ground. Okay. Well, that also kind of gives me the radius then, because if the axle is 15 inches off the ground, from that center to the edge of the tire would be 15. While we're here filling stuff out, why not? Let's get the amplitude. So it looks like it would be 9 in each direction. And that 9 represents the distance from the center axle out to that reflector. Again, I have no idea if we're going to need that, but just in case we do, we've got it. All right, let's see what questions we're getting here. How long does it take for the wheel to make one rotation? So all the way around, 0.6 seconds. What is the diameter of the wheel? So from edge to edge, not the reflector, the actual wheel. Well, we already kind of figured out the radius of the wheel was 15. So that means the diameter would have to be 30, and that's inches. What is the amplitude? The amplitude was 9. The equation of the midline, again, we already got that. That was 15. So y equals 15. Ooh, and how fast is Mary traveling? Dang, that's a good one. Here they don't really give us units that we need to deal with. I don't know if we're going inches per second, feet per hour, miles per hour, but here's what I do know. I know she is going 1 revolution in 0.6 seconds. Okay, 1 revolution in 0.6 seconds. Now, 1 revolution is the same as saying the circumference. And circumference is the same as saying 2 pi r. And in this case, that would be 30 pi. So 1 revolution is 30 pi inches in 0.6 seconds. Now let's say we want this, let's go miles per hour. That's a pretty commonly used unit. Let's say I want to convert this thing to miles per hour. What I need to do is figure out how to get my inches turned into miles and then seconds turned into hours. And you may have seen this in like a chemistry class when you're doing conversions. But if I want to convert out of inches, if I see inches in the top here, if I want to convert out of it, I'm going to put inches down here. And I don't know how many inches are in a mile, so I can't put miles up there. But I could put feet, because I know how many inches go in a foot. And there's 12 inches for 1 foot. This fraction right here is technically, it has a value of 1. So I'm multiplying by 1. I'm not changing anything, but my 1 is being disguised in a very clever manner. All right, so what happens there is I no longer talk about inches. Now I'm talking about feet. But hey, I don't want feet. I want miles. So let's convert out of feet. That'll go in the bottom and into miles. Well, there are 5,280 feet for every 1 mile. So now I'm out of feet because the feet units cancel, and I'm in miles, and I want to be in miles. So right now my units are talking about miles per second. Well, I don't want per second, I want per hour. So now let's get away from seconds. Right here, seconds is in the bottom, so if I wanted to cancel that out, I'd have to put seconds in the top. And I can convert seconds to minutes fairly easily. There's 60 seconds in 1 minute. So now the seconds will cancel. So right now my units are miles per minute. And throw that into miles per hour. Let's see, I'd have to put minutes up top to cancel those away. And then hour down below. And there are 60 minutes in 1 hour. All right, so this goes straight into the calculator. So essentially what we're doing on a calculator, what you're going to punch in, I'll throw it here in fuchsia, is you're going to do 30 pi times 60 times 60, divide that by 0.6 times 12 times 5280. And that will tell you your answer in miles per hour. So I'm going to go ahead and do that on my calculator. Hopefully I don't hit a wrong button here, but you never know. And I am getting 8.92 miles per hour. So not too terribly fast. All right. Onward. Now let's start talking about angles in something called standard position. If you need to pause the video here, that might not be a bad idea to jot some of this down. So angles can be drawn in something called standard position when the vertex of our angle is at the origin. You're going to have one side, we call this the initial side of your angle, is always on the positive x-axis portion. And then your other side of the angle, we call it the terminal side, rotates counterclockwise. So we go through quadrants 1, 2, 3, 4, counterclockwise to get to your terminal side. So for those of you who ever wondered, why are the quadrants numbered like that? 1, 2, 3, 4. Because that's the order our angles would have traveled. All right. So if I have an angle that's, say, anywhere in quadrant 1, that angle measure would be somewhere between 0 and 90 degrees, because 90 degrees would be right up here. If I had an angle that was anywhere between 90 and 180, it would be over here. 180 to, let's see, this would be 270, and then anywhere between 270 and 360. If you have a positive angle measure, it's going to rotate counterclockwise. So it goes through the quadrants, 1, 2, 3, 4. If you have a negative angle, it goes backwards. It goes clockwise, so it goes 4, 3, 2, 1 through the quadrants. So here we can see kind of the difference between a positive 120 degrees. So I'd start at the x-axis and I rotate up through quadrant 1 into quadrant 2, because 120 is somewhere beyond 90, but not quite to 180. Counterclockwise, negative 120, I would go backwards. So I go backwards, here's negative 90. Negative 120 would be somewhere between negative 90 and negative 180. In case you need to know which angles go where, if you want to sketch this out, you might want to have those values memorized. 0, 90, 180, 270. Basically, we're just counting up by 90s. And then you'll notice at 0, that's also the same as 360. We kind of start over again. And that's going to be a theme here with periodic functions. Every 360 degrees, we're going to start over. That process starts over. Negative angles just go backwards. So the 90 is down here now. 270 is up top. Okay, let's take a look-see days. Oh, number 1. It says we're going in a positive direction, so I know it's a positive angle. And it goes up to the positive y-axis, so that would be a 90-degree angle. Number 2, they don't tell me an angle measure. I know it's going to be something bigger than 180 degrees, but not quite 270 degrees. And they're telling me that the coordinates are negative 2, comma, negative 2. So if I think of like a little triangle drawn in here, I went backwards negative 2 and I went down negative 2. Well, if I have a triangle, and this would be a right triangle, where the two legs are the same measure, hopefully we remember that would be a 45-degree angle there, right? That's a 45, 45, 90. So if I wanted this overall angle measure, I've already gone to the full 180, and then we went past that 45 degrees. So my angle measure, we went the full 180, and then we went an additional 45. That would be 225 degrees. Number 3, very same thing. They give us a coordinate. So I know that this would be a 45-degree angle here. And we're going backwards, right? This one, the arrow says we're going backwards. So I'm going to have a negative angle. So I've gone beyond negative 90, but not quite to negative 180. In fact, I just missed that negative 180 by 45 degrees. So I want 45 degrees past negative 90. 45 degrees past negative 90, or 45 degrees just shy of 180. You can think of it that way as well. We would get negative 135 for that one. One thing I should say, and this will come up later, whenever I draw in these little triangles, it always goes to the x-axis, never to the y-axis. So I always refer to the x-axis, never the y. All right, number 4. I'm assuming we're going in the positive direction. It doesn't give me an arrow for directionality here, so it doesn't tell me are we going that way or are we going around that way. I guess we could make the argument based on this arrow that we would have to go down and around. So actually, I'm going to assume that it's a negative angle. So similarly, we've gone past 180 by 45 degrees in the negative direction, so that'd be negative 225. Okay. And we're going to end out here drawing angles in standard position. Now, all of these angles will start off with their initial side on that positive x-axis. So one of the legs of this angle will start off on the positive x-axis. Now, for 36 degrees, if I think of these coordinates of having 90, 180, 270, and then this would be 0, 360, 36 degrees, if I'm going around in a positive direction, it's not going to get to the 90 degrees. So it has to be somewhere in quadrant 1. So here's how we draw it. Bam. Draw your little arrow for direction. That's it. If I do 315, I'd go past 90. I'd go past 180. I'd go past 270. But I wouldn't quite get to 360. So somewhere in here, quadrant 4, bam. Negative 150. So negative means I'm going backwards. I'm going down and around. I'd go past the 90, but not quite to the 180. So it'd be somewhere in quadrant 3. Throw the direction of rotation. 85 degrees would be somewhere up in quadrant 1. Negative 275. So negative means I go backwards. Past 90, past 180, just slightly past the negative 270. So that would be right about there, if I were to guess. And we draw that angle of directional movement. Ooh, 600. 600 did not show up as one of our options. Well, here's the deal. 600 is really the same as saying 360 plus 240. Now, the reason why I'm saying 360 is that means we have one full rotation. So we're going to go one full rotation around and then an additional 240 degrees. So the angle measure for 600, we go past 90, past 180, past 270, past 360, past this would be 540, past this would be, oh no, this would be 540. Not quite 720, which would be over here. So if I go past 360 by an additional 240 degrees, I'm going to be down in quadrant 3. But now when I sketch in my direction of movement, I actually have to mark that we zipped around one full rotation and then ended on that terminal side. Makes it a fun little snail. For those of you who have trouble with kind of these bigger values, and this will only apply to some folks, the way I honestly remember these is when I was younger, I was really big into like the skateboarding, snowboarding games. So I remember, watching people do all these tricks. So I kind of automatically knew these angle measures. If you see a skater do a 360 or a snowboarder's doing a 720 backflip or something like that. So if you're into the skate snowboard culture, some of those angle measures might look awfully familiar. All right, that's it. That's all. You know the drill. If you have any questions, please do not hesitate to ask. And as always, folks, good luck, have fun, be safe, roll tide.